Hey guys, welcome to Applications of Integration, motion of a particle along a line. This is a second video. This video is going to talk about an example where we talk about total distance and displacement, and they are not the same thing. So the example that we're going to try is from the Barron's Guide. It's on page 348 of, I think, the 2012 Barron's Guide. So a particle moves along the x-axis so that its velocity at time t is given by this function, v of t equals 6t squared minus 18t plus 12. Part A, find the total distance covered between 0 and 4 seconds. Now, I've gone ahead and graphed the velocity function. Now, if you're able to use the graphing calculator, it's nice to have a visual representation because you can see what's going on. Now, when we talk about total distance, remember we're talking about the absolute value of a to b of some velocity function, okay, and it's the absolute value, the absolute value of the velocity, which is speed. So the idea here is if I'm looking at this function, if I look between 1 and 2, I notice that before 1 second, the velocity is positive. After 2 seconds, the velocity is positive. And in between here, our velocity is negative. So we know that when t is less than 1, v of t is greater than 0. Now, if I didn't have a graphing calculator, I could factor this and go ahead and use a sign analysis. So between 1 and 2 seconds, okay, we know that v of t is less than 0. It's negative, so it's moving left. And then when t is greater than 2, v of t is positive again, greater than 0. So we can actually set up the integral in 3 parts. We can look at our time intervals, so we can go from 0 to 1, okay, because we're going from 0 to 4 on time, and we can just integrate v of t dt. We do not need absolute value here, even though we're finding total distance, because on the interval from 0 to 1, our velocity is always positive, so we don't need the absolute values. However, between 1 and 2, velocity is negative, or less than 0, so we're going to make a minus sign, and we're going to go between 1 and 2, and we're going to go v of t again. We're going to integrate v of t. Now, because we take the opposite, we're actually going to get the total distance. And finally, between 2 and 4, the velocity is always positive, so we're going to integrate v of t. Again, we don't need absolute value bars on the first integral and the last integral here, because on those intervals from 0 to 1, 2 to 4, the velocity is always positive, okay? And remember, if the velocity is negative, you can take its opposite sign and get the velocity. So the idea here is if we substitute v of t in, okay, I could go ahead and integrate all 3 of these. Now, if we integrated just straight up v of t dt, okay, that means we're going to integrate 6t cubed, put a parenthesis there, minus 18t plus 12. Okay, now that tells me, with respect to dt, and that tells me we're going to get 2t cubed minus 9t squared plus 12t. Okay, and that goes for each one of those integrals from 1 to 2. So what we're going to do here is we know that if we have 2t cubed, that's v of t, that's the integral of that. We have to evaluate each of our integrals from the previous page with respect to the limits of integration. Now, the first one was from 0 to 1. Remember, then we're going to subtract off 2t cubed minus 9t squared plus 12t, and that was from 1 to 2. And then we're going to add to that 2t cubed. Well, not add to it, excuse me. We're going to evaluate and simplify and combine like terms. Now we're going from 2 to 4. And when you do that, when you plug in 1 here, and you plug in 0, and you plug in 2, and you plug in 1, and you apply the fundamental theorem of calculus, you're going to end up getting 34 units. That's the total distance the particle traveled during or between 0 and 4 seconds. Now, when you talk displacement, you're talking about the net change, the net distance. How, overall, where does the particle end up? It's not talking total distance, so it's not the same. So what we can do is just apply the fundamental theorem of calculus from 0 to 4 on our function v of t. That's going to give us an accumulation over time. In this case, it's between 0 and 4 seconds. And it's not going to give us the total distance. We don't want that. So we're going to have 6t cubed minus 12 or minus 18t plus 12. Okay, and that's from we're integrating with respect to dt. We already know what that integral is. It's 2t cubed minus 9t squared plus 12t. And now we have to evaluate our integral from 0 to 4. Don't worry about 4 because each term has a t in it. So if we subtract f of 0, it's going to be 0. When you plug in 4 for t for each one of these, the three terms you get are 128 minus 144 plus 48. Okay, which gives us a total of 32. This tells us the particle is 32 units, so the particle is 32 units to the right of where we started. Where it started, okay? Okay, so that is a second example of particles in motion along a line when you talk about displacement and total distance. So if you guys have any questions or comments, let me know, and we'll see you next time.